move on. Okay, so one of my 2 carbohydrates that I'm going to use for glycolysis. Glucose. Glycogen. Good. Okay. Remember that taking glucose from the bloodstream and breaking it down to start into the chain takes 1 ATP. All right, so we lose an ATP there. We lose another ATP during the straight chain phase. All right. When we move glycogen from stores in the muscle tissue and we break it breaks down to the first molecule in the chain. So we don't need any ATP for glycogen. All right? And then how many carbons do these have? 6 carbons. All right? So at around midway, we break a 6-carbon molecule into 2 3-carbon molecules. All right, and then when we're in the second half of the chain, we start to actually produce ATP. So one of the 3 carbons molecules produces 2 ATP, the other 3 carbons also produces 2 ATP. What do we end up with at the end of the chain? Pyruvate. Good. Okay. We also give off hydrogens. Remember, hydrogens are a problem because they're acidic. All right, so these hydrogens can cause a lot of trouble within the cell because our enzymes that are working at each of these 10 steps to get us from glucose or glycogen down to pyruvate don't like big swings in pH. Okay? So we're going to talk today about how do we get rid of some of these hydrogens. Right? Okay, so our pyruvate, remember that system 1 and system 2 are anaerobic. Okay? So up to this point, we don't need any oxygen available in order to produce a little bit of ATP. We can't produce piles of it, but we can get enough to get us through to that 2.5–3 minute window. Okay? So sometimes then that hydrogen if we're not working with oxygen, that hydrogen is going to get picked up by pyruvate and turned into lactate. Lactic acid first. Lactic acid is very unstable, so it very quickly turns into lactate, and then lactate gets shuttled off into the bloodstream. So if it's following this route, we're working anaerobically. Okay? And that lactate can be recycled back to glucose to provide energy again. All right, but we're not going to worry about that additional system because that's more advanced. Okay, just know that it can. All right. If we're going to be working aerobically, so that we are working for longer than 3 minutes, then my carbohydrate can be shuttled elsewhere in the muscle cell and be used to fuel aerobic metabolism. Okay. Everybody okay with that idea? No. Come on. Questions on this? A little bit simpler than the biology version. All right, so we start off with glucose or glycogen. If we start with glucose, because we have to use an ATP to get glucose into the chain, we only get a net effect of 2 ATP per molecule of glucose. If we start off with glycogen, we get a net effect of 3 molecules of ATP. Okay. But these hydrogens are problematic. Right? Not all of them can get picked up by the pyruvate and turned into lactate. Okay? So we have another system in place. And the other system is a couple of molecules called NAD and FAD. Okay? NAD and FAD. NAD is short for something like nicotinamide adenine dinucleotide or something very long and ugly. All right? NAD and FAD are fine. Here's the trick, right? If you remember NAD and you need to know the long version, you can look it up, right? Whereas if you have to learn the big long word, you might just forget it. So if I were you, I wouldn't bother learning the big long words because they get a bit confusing. Okay? NAD and FAD act like a bus system. All right? And they pick up the hydrogen ions and remove them to another area of the muscle cell. All right? So they're going to take these hydrogens away somewhere else. Okay? That's really useful because that helps to maintain homeostasis within the cell, and we don't see such a large increase in acidity within the cell. All right? And we're going to come back to these hydrogens that have been shuttled when we get to system 3. Right? So if we're working anaerobically, we're relying on pyruvate to pick up hydrogen and shuttle lactate into the bloodstream, which helps, but it can't last for very long. Right? We don't get rid of enough hydrogen that way to keep the balance of the pH within the cell. And so gradually, while we're working anaerobically, we're building up acid levels and we end up seeing fatigue. So I can't run 800 meters as fast as I can run 100 meters, right? Because I slow down over time. Does that make sense? Once we switch to system 3 and we're working aerobically, then glycolysis can just keep going at breaking down carbohydrate because these hydrogens are being shuttled off and taken away. Right? So for glycolysis to continue, we need those hydrogens removed from the immediate environment. Question. Okay, so on to the fun bit. Right? So what happens then if we are training this system, if the event that we compete in uses system 2 predominantly for ATP? So that is going to be an event that is somewhere between 25 seconds to 2.5, 3 minutes long. Right? If it's under 25 seconds, it's going to be predominantly system 1. Between 25 seconds and 2.5 minutes, it's going to be predominantly glycolysis. Right? So as we saw with system 1, if we can increase enzyme activity or enzyme level, then we ought to get a little bit more ATP. And or if we can increase substrate availability, we ought to be able to get a little bit more ATP within our 2.5 minutes. Okay. When we look at glycolysis, though, we have a third factor that we have to take into account, and that's this hydrogen situation. All right? So what happens adaptation-wise to help us with the acidic levels? All right? So the first one, glycolytic enzymes. Okay. As we saw before, there's quite a lot of mismatch in the research. We don't have a totally clear picture of what's going on with the enzymes. So if we can increase the amount of enzymes available, we do see that in some of the research, right? So certain studies show that glycolytic enzyme levels increase. Some say it doesn't. When they're looking at endurance training, for example, the studies that are shorter, that are only 2 months or 3 months long, they don't see a lot of changes in these glycolytic enzymes. But if the study is 6 months long, then we see changes. So it could be that the level of training or the amount of training or the intensity of training, right? There's all these factors that are going to play a role that might be driving whether or not we see these increased levels or increased activity in these enzymes. The researchers study the enzymes in particular to see whether certain enzymes are A, more important, and B, increase more. So glycogen phosphorylase works right up here when glycogen is being broken down to the first level of the chain, all right? So there's been some study looking at that because people were interested to see whether or not levels of glycogen phosphorylase meant that glycogen got broken down quicker and made available to the chain more promptly, right? Lactate dehydrogenase works in here, turning pyruvate, facilitating the change from pyruvate to lactate. Again, people have been interested looking at that because if I can turn more pyruvate into lactate, that means I'm picking up more hydrogens and I'm aiding the environment within the cell. The most important enzyme in the glycolytic chain, though, is phosphofructokinase, and you might see that labeled as PFK. Okay? PFK occurs a step above the split into 2,3 carbon molecules. So PFK occurs somewhere, PFK occurs somewhere around there. Right? And PFK is called a rate-limiting enzyme. that means that without PFK, the system can't work properly. All right? So it's the key enzyme in the chain. So, again, the research is a little bit uneven, right? If we can increase enzyme activity, then that could improve performance in certain events, right? But as I said, there's so many variables involved in the research looking at the changes in the enzymes. It's difficult at the moment to tease out which variable is really impacting the change in the enzymes. So again, we've still got a lot to learn here, right? One of the interesting things about PFK is when they look at muscle hypertrophy, so they look at athletes who are training to add on muscle mass, what they don't always see is an additional increase in levels of PFK. So that extra muscle mass actually ends up diluting PFK, which would slow down glycolysis. So that seems like an odd response to me, because I'm putting on more muscle mass, which ought to improve performance, but I'm decreasing how effective PFK can be within that additional muscle mass. So it seems to me like there's a bit of a hole there in that research, because that doesn't tie up. That would mean that if I put on more muscle mass, I would get slower, not because I'm carrying more weight, but because my glycolytic chain can't produce ATP as effectively. And I'm not sure that that's what we see happen in athletes who are training for muscle mass. So I'm interested to see the next step in the research in this area. So we said to get more ATP out of the system, we have to see 1, glycolytic enzyme changes, 2, substrate changes. Right? So what adaptations do we see to glycogen storage when we train system 2? Right? So we see a much larger store of intramuscular glycogen in athletes who train system 2, also in athletes who train for aerobic events, endurance events, because remember that if we switch to system 3, we're still going to use our carbohydrate from the system. So aerobic events train glycogen storage, and system 2 events train glycogen storage. So I think the problem with the no change in glycogen on sprint activities is because the sprint activities were too short. Right? They were training system 1, not system 2. Or they were doing repetitive sprint bouts, but they were taking too long a rest in between the sprint bouts for it to really hit system 2. So if we do resistance work, if we do longer sprint type training, or if we do endurance training, we see increases in glycogen storage. The more glycogen there is available, the more ATP I can make. So, as I said, we have this third variable here, though. We've got this acidity issue. So the third adaptation that we see when we're training system 2, when we're training glycolysis, is the ability to buffer the hydrogen ions. Okay? So in the UK, the opposite of an acid is an alkaline, but I think over here the opposite of an acid you call an alkaline a base. Is that right? Okay. So alkalines or bases, right? So what we're looking for then is if I'm building up all this acidity on the one hand, I need to provide more base or alkaline to try to balance out the pH so the pH doesn't change too dramatically. Does that make sense? Okay, so not surprisingly, because adaptations are typically positive, right? If I train something, I expect to get better at the thing I'm training, right? So the physiological adaptations are typically positive to enable you to be more efficient at the thing you're training for, right? So we want to be able to buffer these hydrogen ions more effectively, and what we see is an increase in the levels of intracellular buffers. So intracellular buffers can be the inorganic phosphate groups, can be bicarbonate, certain proteins act as buffers, right? And when we do endurance and sprint type training, sprint training within the right time frame, okay, then we see an increase in buffering capabilities. So the longer I can delay the environment turning acidic, the longer I'm delaying the onset of fatigue. Right? So this has led to, and our particular textbook doesn't talk about bicarbonate loading, but other textbooks do. This led to people playing around with the idea of bicarbonate loading, right? If I add bicarbonate as an exogenous source, can I then delay fatigue because that bicarbonate gets to the muscle tissue, right? So, literally, baking soda, right? So, people have used baking soda to try to increase buffering capability, all right? And there's, again, some disagreement in the research about how well that works. Some research says the problem is that bicarbonate doesn't really get into the muscle cell quickly enough, so it takes about 20 seconds to get into the muscle cell, so it takes a while to get there. Some research says no, it clearly makes a difference, and in sprint cycling they've seen improvements of up to like 42 seconds on a sprint time. That's pretty huge, right? So, you know, it's not poisonous, it's not banned, so I guess if you wanted to try it, or if you had a coach that wanted to try it, or you read an article that suggests give it a go, I don't see a problem with it, except that some people have a very adverse gut reaction to bicarbonate of soda, right? So you have to take a lot of it, like 300 milligrams per kilogram of body weight, something like that. It's a lot of baking soda, okay? And then people get cramping and diarrhea and all kinds of side effects. Okay? So the suggestion is to break up your dosage into lots of smaller doses and drink tons of water with it. One of the other suggestions is that you could use citrate instead of bicarbonate, so sodium citrate instead of sodium bicarbonate. And that apparently doesn't have quite as bad an effect on the gut. I would say if you were going to try it, maybe try it a long time away from any important training or competition, so that if you're one of the people that gets these bad side effects and cramping and things, it doesn't interfere with an important part of your training cycle. Okay? As I said, it isn't, to my knowledge, it's not poisonous and it isn't banned by anybody. So, you know, give it a go if you want to. Have extra toilet paper on hand. Okay? All right. So, when we introduce these energy systems, it is typical, I haven't seen a textbook that doesn't do it this way, it's typical to look at them as system 1, system 2, system 3, okay? When we do that though, it's very tempting to then consider them as standalone systems. Right? System 1 is only on between 0 and 25 seconds. Then system 1 switches off and system 2 switches on from there to 3 minutes. And then that switches off and system 3 switches on for anything over 3 minutes. That isn't really how it works physiologically. Most of the time, all 3 systems are doing some portion of work. All right? So they're all adding a little bit of ATP. It's just that what we want to concentrate on is which one is predominant at any particular time. Okay. So our anaerobic metabolism, we're looking at high intensity, short duration activity. Okay? If it's really short, it's going to rely on stored ATP and phosphocreatine within the muscle cell. Right? Then if it's a little bit longer than that initial 25 seconds, by about 20 seconds we're starting to switch, and by 30 seconds we're really into predominantly glycolysis. But there are many, many sport events that are less than 25 seconds long, right? Any kind of jumping, any kind of throwing, diving, right? Javelin, shot put, whatever that one is, I can never remember the name of that one. Okay, weightlifting, so if you watch Olympic lifters, those are all system 1 predominantly, right? Very powerful, sudden, short muscle contraction, high force production. Okay. On the other end of the scale, we're going to look at endurance metabolism, right? Aerobic metabolism for events that are longer than 3 minutes, right? And because they are longer, they are necessarily lower intensity than anaerobic events. Now, that isn't to say that someone that is a world-class marathon runner isn't running really fast, right? Compared to what the rest of us could do, that person is running really fast. For that individual, though, that is not super high intensity. Right? And so we start to introduce the idea that people who are really good, world-class athletes are physiologically a little freaky, right? Because they can do something the rest of us can't do no matter how much we train. Okay? Doesn't mean they don't train their buns off, but they're training a system that gives them a physiological advantage. right? It's not just what's going on in here or in here, right? They've got this advantage that the rest of us don't have. If they choose to take the best of that, they've still got to work really hard for it to perform at that level. Okay? So this chart is in your chapter, so you can take a closer look at it. But what it shows you is some estimates of the percentage of systems at any time in an activity. Use it though as a guideline, not as an absolute, right? Because every single person is different. So just because one person starts to use aerobic metabolism at around 2.5 minutes doesn't mean everybody does. Okay? So what we've got here is that something that is 1 to 3 seconds is in the guideline 100% system 1. Right? And there's no aerobic portion. But anything longer than that, we start to see a mix of the systems, and when we get up to 2 hours, now we're looking at 100% aerobic metabolism and no anaerobic metabolism. Unless you sprint into the finish line, right? So if you're running a marathon and you're shoulder and shoulder with your competitor, right? And you're jogging along or sprinting along, right? And the finish line is there and you increase speed, you switch back to system 1, right? Because aerobic metabolism can't provide ATP fast enough for that increase in intensity to sprint in to the line.
So,
Yes.
I'm sure everybody's been in a game or like in a race or something, like when your body feels like it goes jelly, is that when you lose system 1? You can't increase it at all?
2. That's when your glycogen levels have flatlined. So that's why glycogen storage ahead of those kinds of events can prove very beneficial. Endurance athletes will talk about hitting the wall, right? If you're in the weight room and you do a lot of work and then you get halfway through a squat and your knees start going, whoa, you hope that you've got a really good spotter behind you. That's a similar thing, just in a different situation, right? Okay.
So does system 1 just work the same way the whole time when you're really tired like that? System 1 just keeps chugging away?
It's going very gently. It's in the background, adding a little bit of ATP, not a lot. So when you're sitting here, sitting in class is an aerobic activity, right? Which seems a little odd because we consider aerobic work to be running or biking or walking for a long period of time, all right? But consider what you're doing here, okay? You're sitting here, you're using some muscle contraction, particularly of your core, otherwise you'll be falling off your chairs onto the floor, right? So if we had EMG on you, we would see core activation of postural muscles, okay? You're moving your arm and your hands a little bit, but not a lot, right? So what you're doing when you sit in class is low intensity, long duration, because you have to sit here for quite a while listening to me witter on, right? Low intensity, long duration work. Aerobic. Now, do you burn fat sitting here? A little bit, but not enough to make it, right? It's not like you can sit down and get thin, right? Because you're not working at a high enough intensity to impact fat metabolism very much. this idea, but here's the key. Training, you have to train specifically to where your sport lies on this continuum. Right? So if I am a softball player and I run 5 miles every day, that really isn't going to benefit my softball performance, because softball is not an aerobic event, right? So one of the things you want to start thinking about is specificity of training is crucial if you want to see changes in performance, right? So you want to work out what's the percentage of aerobic work necessary to perform in this sport, and what's the percentage of anaerobic work. So let's say it's 80% anaerobic and 20% aerobic. Then your training program should be set up on an 80-20 ratio. Right? So some events, like a football game, goes on forever. Right? So football is a weird game because they never actually do anything for very long, right? And then they stop and they all walk off and they change over, right? So a football play is anaerobic. What's the longest you move for at any one time, Curry?
Like during play, like 13 seconds.
13 seconds, right? It's clearly anaerobic. Every play is anaerobic. But the game has an aerobic element to it because you don't want to be playing the fourth quarter and be tired, right? You want to play the fourth quarter and be fresh enough and strong enough to play as well as you did in the first quarter. Right? So it's a weird game because you've got this odd balance. Most of the game is anaerobic. But if you're aerobically unfit, chances are fourth quarter is going to be not very pretty. Right? So the book gives some tables during the book for you to look at. Oh, I'm a volleyball player, so what's the estimated percentage of aerobic to anaerobic for a volleyball player? Right? If you look online, you can probably find more information about that. But when you go out to work and you're the coach or you're the trainer or you're the teacher, then it's your job to divide up the training program appropriately, specific to what is required for the event. Right? For me, it doesn't matter. I can do what the heck I like when I'm training, and it either does or doesn't match what I didn't on Saturday, because by the end of my snowshoe race on Saturday I thought I was going to die, right? And I think I came in with only 4 people behind me, but I finished. So that's all I cared about, was could I get round the course without giving up halfway, right? So, but it doesn't matter, because I don't care whether I come last or first or halfway, or, right? But when you are training competitors and tiny little margins make a big difference in performance, then this idea of specificity is very important, right? And a lot of coaches mess this up because they have their athletes run and run and run and run and run, but all they have to do is hit a ball. Or I don't mean all like that, but the game is hit a ball, right? So why do I need to run for hours on end? It's pointless, right? And then this is just another kind of visual to that. So this is for a 3-second sprint. About 55% of your ATP is coming from phosphocreatine, 32% is coming from your stored ATP. we've got a little bit of lactate glucose and about 3% aerobic metabolism, right? But that's only a 3-second sprint. The longer I go, the smaller the red and green get, the bigger the others get. Okay? Question? All right, so on Wednesday, we will start aerobic metabolism. So it's really important that you review anaerobic metabolism, make sure that you understand the process before I chuck on the next piece of the pie. All right? I want to start Wednesday with questions on anaerobic metabolism if anybody has them. All right? So that we're totally clear on System 1 and System 2 before we start off on System 3. Good.